Hello. Today we're doing a lesson on number sets. This is a new unit. Some of these units are a bit weird because they don't really seem to follow an order, but it's all to do with like cyclic progression, and over time I hope that it makes a lot more sense. This meme on the left isn't really a meme, it's actually rather what we're doing today, and as you'll see, we'll talk about natural numbers, whole numbers, integers, real numbers, and then this big thing. Kind of like use this in your mind while we go through this, because that's kind of what everything you need to know is basically in that one picture. Okay, anyway, right. Genuine question. How many numbers do you think there are between 0 and 10? Now, some people say like 9, right? They go, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's between 0 and 10. You could also include 0 and 10, I guess, which would be another two numbers. But then the question is, okay, is there only 11 numbers? And then I ask the question, what about 3.2? So a lot of people go, 9 numbers, right? Because 1, 2, 3, etc., etc. And then other people go, 11, because you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 0, 1, ... 9, 10. If you say between, I don't know, some people include that, right? But then I go, okay, what about, like, I don't know, what about the number 3.4? Is that a number? And if you go, yeah, well, that is a number, you go, okay, so there's more than 10 or 11, isn't there? And then you go, okay, maybe there's 110, because maybe it includes like all decimals, so like 3.2 and 3.3. I don't know why I've started here, it's terrible. And then that goes all the way up, maybe 110. But then you start to realize, okay, what about 3.02? And then what about 3.002? And surely after that, you no matter how many numbers you say there are, I can just add another decimal point and get another whole bunch of numbers, right? So the answer here is how many numbers between 0 and 10 are infinity. And then I go, okay, well, how many numbers are there between 0 and 1? And then you go, infinity. And I go, okay, and what about 0 and 2? And you go, infinity. And then you go, well, does that mean they have the same amount in them? Or does that mean there's one infinity that's bigger than another? And I thought infinity was supposed to have an uncounted number, but then you have the two different size infinities, or the infinite different size infinities. That kind of question and that kind of thinking is where you will at some point end up throughout this course, and if not this course, then your grade 10 teacher, right? So hopefully that makes sense. It's just more of a thinking thing, and me just trying to open up the world that is maybe you haven't been able to think about some of these things before until someone pushed you to it. And now we're here and you're like, okay, the world is wild. Anyway, let's talk about sets. So what are sets? Ignore the images for a second. Simply put, a set is a collection, right? So it's a collection of things, and they share a thing, and everything in that set shares that thing. So, for example, things you wear, right? You could wear a hat, a shirt, a jacket, socks, shoes, etc., etc., etc. And note how when I put these 3 dots here, I'm basically saying, there's a bunch of different kind of options here, but I don't have to show you all the options. You could carry this on this list because you know what I'm doing here. Hat, shirt, jacket, so you know maybe some more items you could add on. And so those dots there are telling you there's more to come, but I'm hoping you could figure that out. Whereas fingers, if I say fingers, I go index, middle, ring, and pinky. Those are your 4 fingers. And there are no dots here because there are no other things it could be, right? So again, the 3 dots there are kind of just showing you there's more stuff to come, potentially infinite stuff to come. Cool. So here's the notation then. So first of all, each thing that we list is either an element or a member, right? So they're all elements or they're all members, and they're all separated by a comma. That's pretty obvious, right? Because if I didn't have a comma, it would look like, well, just in the bottom, that would be 3, 6, 91, which is not what we've tried doing. It's 3 and 6 and 91, etc., etc. We use curly brackets. Listen, people call them set brackets, people call them braces. Just in general, know that if they start and end with that, it's denoting that we're in a set. And nobody's like bothered about how pretty your curly brackets are. As long as you know curly brackets, that's for sets. As you can see at the bottom, I've got 3, 6, 91, 3 dots meaning it goes on forever and infinite, like I said a second ago. And then we have an element or member meaning the same thing. That's right, as I said, element, member. There's different names for them, that's fine. Different types of sets then. So if I wrote out all the numbers, well, in a world that I could, right? Obviously I can't do that. But if I wrote out, let's say, all the positive integers, right? What I'll do then is I'll do 1, 2, 3, 4, 5, and then I'll put 3 dots there. As again, those 3 dots shows that this goes on forever, and this kind of set is an infinite set, right? Because it goes on forever. There's literally 789, 165 million. You get the idea. That's all it does. If I wanted to write out all the letters, though, I might go A, B, C, dot, 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 X, Y, Z. And here, what I've done is the dots in the middle don't mean it goes on forever, right? It means that, listen, I've shown you what's going to be in here. I'm hoping you can fill in the middle. I don't need to fill it in. The ellipses show that there is stuff in the middle, but it's not infinite. It's a finite set, finite being the opposite of infinite, right? And they are an only, so because we only know there's 26 letters, so it definitely has a finite number. Okay, so if there are sets, there are also subsets. Now, in general, if you see the word sub, it normally means inside or less than or something like that, right? So a subset is a set that's inside a set. Cool? An example of that then, if I said the integers from 1 to 10, you'd be like, hey, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I then said, oh, okay, what about the even numbers at 1 to 10? That is 2, 4, 6, 8, 10. The most important thing here then is this is a subset of the one we have above because all of the numbers I have here are in here, right? If this subset had like a 0 here or a 12 or something like that, this would suddenly not become a subset. It'd be its own set and it wouldn't be a subset of the one above. Another subset, for example, could be 1, right? Because we have all the subsets with only one. I'm just going to erase this very quickly to make sure it's not confusing. Subsets can only have one member. Subsets can actually have no members. But that's an interesting convoluted conversation. But there is such a thing as a set with 0 numbers or 0 things in it. That's fine. There's nothing wrong with that. But a subset can easily just be one number. Okay, so there are a bunch of questions here. Have a go at them, and you know how it works. Like pause it here, and then we'll talk about it. What I will say before you go, and that's probably the worst time to say it because you probably paused it by now, is when it says state the number of elements, it literally wants a number, yeah? So it wants how many are there. It's not a trick question, just how many. Okay, let's pause it now, and I'll have a go. Okie dokie. So state the number of elements in each set. All we're doing then is a blue, green, red, and yellow. Like when I teach this in class, a lot of people go, oh, is it trying to do all the colors of the rainbow? No. If there's no ... there anywhere, it's saying that's your set. So this is quite literally 4. In the same way, there's 7 letters there, so that's 7. You would see Ontario, Alberta, and Manitoba thinking, oh, maybe they're provinces. Maybe there's more that I can list. No, there's not. If it's beginning and end with no dots, we just say that's how many there are. So there's 3 there, there's 5 there, there's 3 there, there's 2 there, there's 1 there, and then here, 1, 2, 3, 4, 5 with ... you should say there's infinite. And then you should say there's 0, there's nothing in there. As I said earlier, that's absolutely fine. Explain why the set 7, 9, 12 is a subset. I'm hoping you look at 7, 9, and 12, 7, 9, and 12, 7, 9, and 12, and see that all of the parts of this set are in that set, and say something like that. So all the, and let's try to use their language, members of this set are in the bigger set. And so basically what you're saying there, it's a subset because it shares all the same members. So that's there it is. This has 3 members. That one has all the members that this one has. Explain why the set 0, 1, 4, 9, 16 is not a subset, and quite literally, it's this number right here, isn't it? 0. There is no 0 here. It has 1, it has 4, it's obviously going to have 9 and 16 over here somewhere, right? But it doesn't have 0. So 0 isn't in the larger set. So it's not a subset. It's not is a word we want. Not a subset. Not a subset. Honestly, my writing today is just appalling. Okay. And then, last but not least, we're looking for anything on the right. It says match the pairing set, which is on the left, with the corresponding subset on the right. So we're looking on the right and we're saying, okay, which one do these go to, right? So -8, 7, -8, -6, -5. I'm saying that this one goes to this one because they literally have all of the same parts, right? All the same parts. -8, -6, -4, -2. Where do we have that? Well, -13 belongs in that, doesn't it? No, it doesn't. Hold on. 0, 2, 4, 6, 8 is going to belong on that. Sorry, I'm looking at the wrong thing. The reason for that, even though this has 4 things before it, it still does have are 0, 2, 4, 6, 8, ... And this is what this one has. So that's good. 1, 2, 3, 4, 5, ... Even though this is all the numbers and this one has only odd numbers, it does include it. And then is negative 13 going to be in this set? And I haven't shown you this, but you see how the ... at the beginning? That's saying that that's all the numbers before it as well. So you can see the pattern, negative 1, negative 3, negative 5. We can obviously see it's odd numbers, and we can see negative 13 is an odd number. So there we go. Okay, if you got all of that right, you're the best. If you didn't, that's okay. Let me know by email. Let's move on. And there's some answers there as well. I don't know. Some people prefer the answers and don't have to wait for me, but all right. Okay, so what about numbers? So numbers, a bunch of mathematicians basically got together and they looked at how numbers are operated, and they were like, okay, we're going to put these into some groups. And they decided the groups. And unfortunately, we don't get a say in that. We just have to learn what these sets/groups are, right? They defined these rules. They defined these sets. And this is one of those things you just have to learn. But hopefully I can try explain it in a way that makes sense why the system's the way it is. Here we go. So there's a lot of information here. I'm not expecting you to know it all right? Okay, natural numbers. So if you think back to when we first created numbers, right? And we're like, oh, I want to buy your cows. Right? You'd be like, oh, how many cows do you want me to buy? I'd like, I don't know, I'd buy 1, 2, 3, 4, 5. I'd buy a certain amount of cows, right? These are your counting numbers. So these are actually real things, right? These are things that actually make sense in life. They have the letter N. Don't worry about that in grade 9. Very rarely do people ask what the letter is going to be. But as you get to grade 10 and grade 11, you will start having to use these letters. And on a number line, it looks like this, right? So the standard natural numbers, they're the numbers that actually allow me to count something. Wonderful. Cool. Then we have whole numbers. You go, oh, okay, I'll buy 4 of your cows. Oh, you buy 4 of my cows? That's going to leave me with no cows. Okay, so then we must include the number 0. So the next group of sets is the whole numbers, right? It's exactly the same as natural numbers, but it also includes 0, and that's basically the only difference. And again, there's a W there, and there's a W, right? Whole numbers, whole numbers. And on number line, there it goes. So it has the 1, 2, 3, 4, but it also has the 0. And then you go to a guy, you go, well, hold on. If I'm pretty sure you said you were going to sell me 2 cows. You owe me 2 cows, but I don't have them right now, so I'm down 2 cows. Okay, so now we're going to include negative numbers. I don't know my obsession with cows today. So we have the natural numbers, then we have the whole numbers, and now we have the integers, which also include negative numbers, right? So it's still the exact same. They're still the counting numbers, but now we've got 0 included, and now we've got the negative direction as well. But it still includes all of them, right? Again, integers, right? And again, that's what the number line looks like. And then at some point, we started to be like, well, hold on. If I want to trade my cows, but I only have sheep, my cows aren't worth, it's not 1 to 1. There must be like a number in between the value that I must be able to say what all your things are. And that's when we get to rational numbers. So we have all the like numbers, right? And now we're looking, okay, what about in between them, right? So any number that can be written as a fraction is a rational number. And so that includes everything we've done so far, right? Because -7, for example, can just be written as -14/2, right? Like 3.2 can be written as 32/10. 0.875 is 875/1000. These are all numbers can be written as well, not all numbers can, but like all the numbers that can be written as a fraction are rational. And that's basically most of them, if not all of them. It's not all of them, but if not very close to, right? So rational numbers are basically everything. And then the ones that are weird, the ones that aren't rational, those are called irrational. And these are numbers that go on forever. And so these are famous numbers like pi, right? Pi is 3.141. I'm not reading all of that, but the point is it goes on forever, never terminates. If it never terminates and it doesn't repeat, we can't write it as a fraction. There's no way to do that. So if it's like something like pi or the square root of 2, which is also some horrific thing, right? Or any square root of any number that's not a nice number, like being a square, they are all irrational. So we have rational and irrational are complete opposites. Rational are fractions. Anything can be written as a fraction. And the other ones are irrational and they can't be written as fractions. Now what that looks like then is if you put rational and irrational together, you end up having real. And that's it. We do have something like non-real numbers, but again, you won't even get close to this before you get to university, really. So don't even worry about the non-real or imaginary or whatever. And here's some examples. Infinity, not a real number, can't even talk about it. And the root of -1, there is no number that multiplies by itself to get -1. So therefore it doesn't exist in the normal term of what we're talking about. Anyway, ignore that. Let's talk about how this all fits together. So this image, genuinely, any assessments or any tests that we do on this kind of stuff, I would have this image available. In fact, I would probably print this image and have it somewhere in the room just so I understand life. Maybe draw my own one, I don't know. As you can see, natural numbers are inside whole numbers. So natural number is a subset of a whole number. That subset of an integer, that's a subset of irrational numbers, and they all are subsets of real. In the same light, irrational numbers are a subset of real as well. Rational numbers and irrational numbers make real numbers. What kind of questions can you get, especially through like if you're doing EQAO this year or any of those kind of things? What kind of questions can you get? It's stuff like, oh, can you give me a number that is only a part of 2 sets? And then what you might do is realize that, well, real numbers, all of them would belong in real. So no matter what, everything that you know belongs in real. And then what you want to do is you want to pick like an irrational number. So if you pick pi, you'd be like, oh, that belongs to 2 sets. That's a rational and real number. Another one might be like, hey, the number 3. How many sets does a number 3 go into? And then you'd be like, well, okay, well, it's part of this set, and 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 it's part of that set. So you would say, and you can use the letters if you wanted to, but you would say it's part of natural numbers, part of whole numbers, right? So those are kind of questions that you have to be used to. And if you have a look at these questions here, that is literally what it is. So I'm going to go through these, and then I'm going to put these questions up, and then wait, and then go through them. And then I'm going to go through these, wait, and go through them. And if you want to just speed ahead, there's a bunch of examples there, but I find that people like when I do it. I don't know. Let's have a go. So, list the set of natural numbers less than or equal to 11. So remember, natural numbers, here they are, right? They are all the numbers that are positive, that are like whole numbers, if you will. I know, if you're saying the word whole, and just the countable numbers. So all the numbers less than or equal to 11, I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nothing wrong with that. Those are all the natural numbers. However, bearing in mind that what I've just been through about sets and stuff, and that's a lot of writing, you can also write that as, sorry, that should, no matter what, I should have this thing. You can also write that as 1, 2, 3, ... 10, 11, right? Saves you doing all the writing, and obviously people know what that is. List a set of whole numbers less than 8. Again, whole numbers are here. So what we're going to do, it's going to be 0, 1, 2, 3, 4, 5, 6, 7, right? Less than 8, so it's not going to include 8. So it's quite literally going to be 0, 1, 2, 6, 7. Excuse me, sorry. And then list a set of even integers from -4 to 2. You know what even is. It's divisible by 2. So we're looking for any even number between -4 and 2. And again, integers include negative numbers. So it's going to be -4, -2, 0, and 2. Anyone ever tells you that 0 is not an even number, send them in my direction. I will quite happily tell them they're wrong. Find the number with the following property. Identify the sets where the number belongs. The number belongs to only 2 of the sets above. So you can pick any irrational number, can't you? Any irrational number will only belong to irrational and real. So again, let's pick pi, because that belongs to irrational. What is wrong with me? Irrational. If I could spell, I'd be dangerous. You know what it is? That the T threw me off. I don't know what I was doing. Irrational and real. Right? You could also pick any rational number, couldn't you? As long as it can be written as a fraction and it isn't just like an integer or something. So like 4.2. 4.2 works because 4.2 is a rational number and real. Right? So they only belong to 2 sets. The number belongs to more than 2 sets. I don't know. 1. Because 1 belongs to natural numbers, whole numbers, integers, rational numbers, and real numbers. That's supposed to be a Q. And then real numbers, I know it's annoying, rational numbers have a Q instead. Anyway, hopefully that makes sense. I'm not, as I said earlier, this is not something that you're going to get straight away. So don't worry if you're not, but that's how that works. Right, here is your questions. Have a go at this. I'll go through it very shortly. Okay, hoping that's enough time. So express the following sets and braces. The sets of natural numbers less than 10. So that should be, let's throw the brace out there. Let's go 1, 2, 3, ... 8, 9. Something like that, right? There's supposed to be a comma there. I might just zoom in a bit here, actually. Cool. The set of odd numbers from negative, odd integers. So remember, integers are all the negative and positive not countable numbers. So -5 to 5, we're looking at -5, -3. You can throw some dots in there as well. 3, 5. You can assume people can make that jump, right? It's pretty obvious it's going down in twos. That's all we're really doing. The set of whole numbers are up here. Literally copy and paste 0, 1, 2, ... I didn't know I could do that. That's pretty cool. 0, 1, 2, ... Set of all integers, exactly. Copy it again, like -2, -1, 0, 1, and 2, ... Remember the dots at the beginning and at the end are to show you that it goes on forever. The set of all even whole numbers greater than or equal to 20. So it's all even, so you know it's multiples of 2. Whole numbers, so it's going to be any countable number that could include 0, but then it says greater than or equal to 20. So we're just going to start off 20 and then go 22, 24, 26, and then put a bunch of dots and leave it there. And if you didn't go as high as you could have left it at 24, really. Okay, the set of all integers that are multiples of 5. Integers, look at, if you remember, it goes all the way to negatives and positives. So I would do something like -10, -5, 0, 5, and 10. And then throw out those dots at the end and also at the beginning to let everyone know what's happening. My braces are horrible today. Okay. Identify each of the following statements as true or false. The set of whole numbers is a subset of the real numbers. Yeah, it is. Whole numbers are here. Real numbers are the big thing. So yes, anything smaller is the subset. So this is true. The set of natural numbers is a subset of integers. Yes, it is. Again, natural is smaller than integers. So we'll put a little T there. The set of whole numbers is a subset of natural. No. Whole numbers is bigger than natural, so that is false. The set of rational numbers is a subset of real numbers. That's true, right? Rational numbers are not as big as real. The set of irrational numbers is a subset of rational numbers. That's false. They are literally opposites. You can't have a rational or irrational number the same. The set of prime numbers is a subset of rational numbers. So just a quick one, if you remember what prime is, it's all numbers that can only be divided by itself and 1. So that would start with 2, 3, 5, 7, 11, etc., etc., only divisible by themselves and 1. And what is that a subset? Is it a subset of rational? Yeah, every single prime number can be written as a rational, so that's great. And then 2, 3, and pi is a subset of rational numbers. It would be if it wasn't for pi. The fact that pi is in there means no, false, because pi is irrational. Okay, cool. And then last 3 questions. Here they are. Have a quick go. Okay. Jonas stated that the subsets always have fewer elements than their parent set. Is Jonas' claim correct? This is one of those really annoying questions where Jonas actually incorrect there, because it should have fewer elements. It should, but you can have subsets that are inside parent sets that are the same size. And an example of that is if I picked all the numbers from like 1 to 5, 3, 4, 5, right? And then I was like, hey, can you give me all the numbers in your set that are less than 10? Well, it'd be the same, wouldn't it? And that's annoyingly, it's still a subset of the parent set. It's just, it's just annoying. So is he true? No, he's not. No, annoyingly. But like in my mind, it should be. But like whatever. No, is that what the thing says as well? I think that's what they said as well. Yeah, good. Okay, Aliyah, we're going to go Aliyah. Claims that sets 3, 4, and 5 and 4, 5, 3 are the same. Is she true? Yeah, they're true. It's just ordered differently, isn't it? So yes, just different order. And order doesn't really matter. Order only matters when you have like ellipses and they're showing different things. Describe a real life situation in which you might encounter an irrational number. Literally anything. If you ever have to do Pythagoras is a good example. You will find the square root of stuff, and before you say, are you going to do Pythagoras in real life? Yeah, most engineers or anybody who has to do anything with like building or design will use Pythagoras. A perfect example of this is even TVs, right? TVs, when they count like the screen size, they use Pythagoras to find the screen size, or a tape measure, but they could use Pythagoras. Where else, if you ever want to do anything with a ball or anything, like if you have a rain barrel at home and want to know how tall it will be or how much liquid can fit inside it, because it has a circle, it's going to include pi. So any type of thing of a circle, if you want to have like a frame around a clock, you're going to have to use pi. So basically anywhere you're going to use pi or anywhere you're going to use a square root, you're probably going to find an irrational number. Anyway, okay, hopefully that was helpful. That's it from me. Have a good day. Thanks.